Another day, another story. In the ever-evolving world of physics, there exists a theoretical framework that challenges our understanding of the fundamental building blocks of the universe. Welcome to the intriguing realm of string theory. In traditional particle physics, we often think of particles as tiny, point-like entities. But in string theory, these particles are replaced by one-dimensional objects known as strings. These strings, like cosmic threads, dance through the fabric of space, interacting with one another in ways that defy our classical understanding. On scales larger than the incredibly minuscule string size, a string behaves just like an ordinary particle, complete with its unique properties, all determined by the way it vibrates. It's through these vibrations that the incredible richness of the universe emerges. Among these vibrations, one particular state gives rise to the elusive graviton, the quantum mechanical particle responsible for carrying the force of gravity. Thus, string theory becomes a theory of quantum gravity, bridging the gap between the quantum world and the mysteries of gravity. But string theory is not just one simple idea, it's a vast and varied landscape of possibilities. It seeks to answer some of the deepest questions in physics. String theory has significantly influenced mathematical physics, leading to breakthroughs in areas such as black hole physics, early universe cosmology, nuclear physics, and condensed matter physics. With its potential to unify gravity and particle physics, string theory emerges as a candidate for the coveted theory of everything. A theory that could describe all fundamental forces in matter. However, despite decades of research, we're left with questions. To what extent does string theory describe our universe? How much freedom does it allow in defining its details? String theory's journey began in the late 1960s as an attempt to explain the strong nuclear force, but it soon evolved into a contender for the theory of quantum gravity. From its early days as bosonic string theory, which considered only bosonic particles, it transformed into superstring theory, introducing the concept of supersymmetry, bridging the gap between bosons and fermions. Eventually, 5 consistent versions of superstring theory paved the way for the discovery of M-theory, a tantalizing theory in 11 dimensions that may encompass them all. And in 1997, an incredible revelation known as the ADS-CFT correspondence linked string theory to quantum field theory, opening new doors to understanding our universe. Yet, challenges persist. String theory lacks a universal definition, and it paints a vast landscape of potential universes, making it challenging to connect to our reality. Some within the scientific community raise questions about the value of continued research on string theory unification. In the grand symphony of the cosmos, string theory plays a complex and enigmatic tune, challenging us to explore the depths of reality and the very fabric of the universe. The journey through the microscopic world of string theory continues, promising to unravel the mysteries of the universe, one vibration at a time. Thanks for watching. Comment and subscribe.